In this question, we are told that an astronaut is tethered to a rope and the rope is being drawn towards a surface. So from the perspective of this astronaut, what are the forces that they are feeling? Only one, the tension of the rope. They're in space. There is no other force acting on them. There's no weight force, obviously, since they're far from any celestial body that could provide a weight force that could pull them gravitationally. And they're not resting on a surface, so there's no normal force. So the only force on them is the tension from the tether. Now, let us draw the free body diagram. Or rather, this is the free body diagram. Now let us draw the origin and axes. Origin always goes on the spot, and I'm going to set my axes so that positive x is in the same direction as the tension. Now, in x, we are told that, or we can say that the total force is due only to the tension. But total force is equal to mass times acceleration. Plug in tension for total force. Tension is equal to mass times acceleration. We were told that the tension was 50 newtons. So 50 newtons must be equal to the mass of the astronaut, that was the unknown in this question, that's what we were trying to solve for, multiplied by the acceleration, which was 0.893 meters per second squared. So now we just need our calculator. 50 divided by 0.893 gives us 55.99. I'm feeling lazy, so I'm just going to round that up to 56 kilograms. And now, knowing the tension in the rope and the acceleration of the astronaut, we have worked out the mass of the astronaut. In this question, we are told that a spacecraft, which looks something like this, I know I've ended up making it look like a roller skate, but whatever, is gradually being brought to a stop. Now, if we were to draw the free body diagram of this spacecraft, it was actually given to us, but let's replicate it over here. This is on Earth, so the weight is pointing down. The normal force is pointing up, because that's the support coming from the ground. If there were no normal force, then this would just plummet straight down to the center of the Earth. And finally, there's the actual force which is pushing against it to slow it down. So maybe that's something like air resistance or friction, or maybe there's a parachute behind here. There are, it was not specified what that force was. So let's call this the applied force, which is pointing backwards, like that. Now, I'm going to set my positive x-axis as being rightwards and my positive y-axis as being upwards. Now, there is no motion up or down that is along the y-axis. So there's no acceleration there, and these two forces, normal and weight, are going to cancel out. So for our purposes right now, we're just going to look at the x direction. But if you're so inclined, I'll take a look at normal and weight afterwards. So in the x direction, there is only one force. The total force is equal to the applied force. And because this applied force is pointing backwards, I should strictly write it like this. Negative of the absolute value of applied force. But total force is also equal to mass times acceleration. So that means that the size of that negative applied force is also equal to mass times acceleration. We were told that the mass was 2100. The acceleration is unknown. Or sorry, the acceleration is negative 196. 2100 times negative 196. That negative corresponds to the fact that it's in the negative direction. It's slowing down in the positive direction, so that qualifies as a negative acceleration. So 2100 times 196 gives us 411600. So the applied force is 411600 newtons. And because it's pointed leftwards, that's the negative x direction, I'm going to put it down like that. Negative 411,600 I hat newtons. Now, although the question didn't ask for this, in the y direction, the total force is going to be equal to the normal force pointed up and the weight force pointed down, which I would symbolize like this, plus negative weight force to make sure that we don't run into any questions about signs or anything like that. But in the y direction, the total force is also equal to mass times acceleration. Therefore, normal force plus negative weight is equal to mass times acceleration. Now, this object is not compressing into the ground, and it is not levitating off the ground. So its acceleration in y is 0. So that gives us normal force minus weight force is equal to mass, 2100, times 0, which is 0. How big is the weight? The weight is given by mg, that is mass, 2100, times g, 9.81. And that works out to 20,601. Newtons. So I'm going to write this over here. The weight force should correctly be written as 20,601. This is in the negative j hat direction. And the normal force must exactly balance that out to provide that acceleration of 0. So, although the question didn't ask for it, we have now solved for the force applied, that was the thing that they were actually asking for, but also for the two other forces which this spacecraft is experiencing. In this question, we were given a trampoline and a person who is jumping on said trampoline. Let's draw the force balance in this case. The person would feel a weight downwards. But in order to prevent them from falling down to the surface of the Earth, the trampoline has to support them. But the trampoline has to do more than that. It doesn't just support them, it has to propel them up into the air. It has to accelerate them upwards. So it has to provide a very large normal force in order to do precisely that. I am going to set my origin and my axes like that. So, the total force in the y direction is given by normal force plus negative weight force. Total force is in turn equal to mass times acceleration. So now we can equate these two. The normal force plus the negative of the weight force, or the negative of the absolute value of weight force, is equal to mass times acceleration. Now let's put together everything that we know. We do not know the normal force. This is something that has to be deduced. The weight force, however, can be figured out because the weight force is equal to mass times gravity, which is equal to mass 45 times gravity 9.81, which works out to 441.45. So now let's plug this weight force in for the weight over here. The normal force plus negative 441.45 is equal to the mass we were given as 45, and the acceleration we were told was 7.5 j hat meters per second squared. So j hat obviously because the normal force is going to propel them upwards in the y direction. 45 times 7.5 gives us 337.5. And then that plus 441 plus 0.45 is 778.95. So the normal force being exerted by the trampoline is 778.95 newtons, and this would be in the j hat direction. Notice in this case that the normal force is considerably larger than what the weight was. This makes sense because the normal force has to provide an acceleration, and it has to not only counter the weight force, but also provide an acceleration that is contrary to the weight force, so it has to be much larger. In this question, a gymnast is climbing on a rope. Drawing the free body diagram for this question is actually a little bit more complicated than what it might initially seem. There are only two forces acting on the gymnast, but we need to identify what they are, and that takes a little bit of thought. The gymnast over here is obviously going to be pulled downwards by gravity. That's the weight force. But what is the force that's supporting them? It certainly isn't a normal force because he isn't standing on a surface. There aren't any springs. He isn't being pushed by a jetpack, so there's no force applied. The one thing that we do know is this character is dangling from the rope. He is pulling on the rope, and therefore, by Newton's third law, the rope must be supporting him. So, whenever there's a rope involved, that force is called tension. Again, because he's pulling on the rope must be pushing on him with an equal and opposite force. That's Newton's third law. Now, let us apply the force balance. Or now that we've done the force balance, let us apply the axes. And let us proceed from there. For part A, in the y direction, we know that total force is equal to tension plus negative weight. Total force is, according to Newton's second law, equal to mass times acceleration. So we can combine these to say that tension plus negative weight is equal to mass times acceleration. Now, actually, this part is going to be consistent for both part A and part B. So I'm actually going to write part A down here. In part A, I actually don't even need to do that yet. Why? Because we still need to figure out what the mass is. The weight rather. The weight of our hero is given by mass times gravity mass 60, gravity 9.81, and 60 times 9.81 will give us 588.6. So let's plug in this information into this equation. We would get tension minus 588.6 is equal to 60 times the acceleration. In part A, the acceleration is equal to 0. So that would mean that tension minus 588.6 is equal to 60 times 0, which is 0. So the tension is equal to 588.6 newtons in the j hat direction. Whereas for part B, run out of room here, the acceleration is going to be 1.5. So I'm going to write over here. I would say that tension minus 588.6 is equal to 60 times 1.5. 60 times 1.5 gives us 90 plus 588.6 would give us 678.6. So in this case, the tension would be 678.6 j hat newtons. So if he is not accelerating, the tension in the rope above him would be 588.6 j hat newtons. And if he is accelerating at a rate of 1.5 meters per second squared, the tension above him would be 678.6 j hat. The rope would be stiffer in order to support the acceleration that he's experiencing.